First of all, since we are considering partial derivative, that means we need a function first, but that function will be of more than one variable. So that is like consider a function. Consider a function of two variables, say f x comma y. Okay, so then it means that we need to take partial derivative, right? So since we are defining the function, but it should be defined on a domain where it is defined. So on say x a to b and y is from c to d. All right. So now you can visualize that it is on a square grid. Sorry, in a rectangular grid. Like, so x will be from a to b and y will be from c to d. So it will be this region, right? Yeah. So f is defined, f x comma y is defined on that rectangle. Okay. So for simplicity, just for simplicity, that means x, when we discretize the x-axis, it will be on equally spaced and y-axis also equally spaced. Okay, so for simplicity, let's consider a uniform grid. Okay. So very soon, like you will see that we are going to discretize our data sets. Okay. So that is xi plus 1 minus xi will be again delta x here. Okay. It's up to you how many points you want to take. Like I am taking m points. Confused a bit. I think it should be 1 to m or maybe 0 to m minus 1. Okay, 0 to m minus 1. So it is m points. So similarly, yi plus 1 or yj plus 1, we are considering I in this index for the x coordinate and j index for the y coordinate. So yj plus 1 minus yj is like delta y. J again from 0 to say p minus 1. So it is not necessary that you take the same number of grids for the x and the y. Okay, it can be different set of grids. Okay, but for the x1 should be equally spaced, and for the y1 it should be equally spaced. The number of grids for x and y can be different, but xi minus 1 minus xi should be, the spacing should be the same in x coordinate and the spacing should be same in the y coordinate. It should not matter that the number of grids for x and y should be same. Okay. So how can you write in general? So just to motivate, like we can discretize this grid like this diagram I want to draw. So lot of different points like a grid. Okay. So seems like they are equally spaced, right? So yeah, you can do that. I'm skipping some of the rows. Then maybe I will draw one more. Okay. But just to give you a feel that what is going on. Okay, take any point. Take any point. Like this can be your x equals to a to x equals to b, and similarly we can have the like the y axis as well. Like this guy delta y, and this guy here will be delta x. Right? Clear? You understood the delta x, delta y, right? Okay. Now, if you consider some I comma j, suppose this is I comma j, okay, and you want to take the partial derivatives of with respect to x or with respect to y, then you need four most important points. What are those four most important points? They will be like this: the topmost point, the below point, the left point, and the right point. So those I have marked with a cross. If you are taking if you want some information of derivatives at this point I comma j, you need the information at the left, at the right, at the top, at the bottom. Based on that, we will write our equations. Okay, that's a very fundamental idea regarding partial derivatives. Okay. Okay. Similarly, it will go like y equals to c to y equals to d here. You're discretizing on the y-axis and also on the x-axis. Okay, again, it is discretization. Again, a set of points. Previously, we had a set of points on like interval on one dimension. Now, for a 2D case, like partial derivatives, you are having it on a lattice. Like different points are kept, like in a classroom, you can imagine. Okay. So here the function fx comma y, last time, like while discussing, using the notation of fi, fj, right? Similarly, here we will use the notation fi comma j. What is fi comma j? It is f of xi comma yj, right? How you will get xi? Xi you can write like starting interval x naught plus I minus 1 delta x, comma yj will be starting point is c plus j minus 1 delta y. You are respecting the step size of each of the variable. You cannot write I minus 1 there in y. You have already defined I and j here. So you have to follow that notation here also. Okay. So similarly, like now you can use the notation of like dou f by dou x by dou y. You can even take double derivative, dou f by dou x2, dou f by dou y2. Okay. There can be even mixed derivatives like dou 2f by dou x dou y. Okay. So things get a bit more complicated when there are more than one variable in picture. Okay. So you can derive these formulas, but I won't go into the derivation. It will be, you can do it. You can spend time, but it will be very similar as you do forward difference. Okay. So I will just write the formula so that you can appreciate the one-dimensional like forward finite difference and backward finite difference. Okay. So dou f by dou x, and of course you have to evaluate at some grid point, that is I comma j grid point. Okay, I comma j, that means ith point in the x-axis, jth point in the y-axis, and then you define which is the point, grid size, grid point, I comma j. Okay. And since we are differentiating with respect to x, okay, so only thing that will change is the ith index. Ith index. So you can see 1 comma j minus fij, okay, by you, or should I divide it by del x or del y? Yes, because you are differentiating with respect to x. So you have to consider the step size of the x grid. Okay. So then it will be order of delta x. Okay. So this is like the forward difference formula. Okay. But in the case of your finite, in case of like partial derivatives, like function with more than one variable. Okay. So you can appreciate this while learning the forward finite difference. You see the similarity, right? How do you see the similarity? You can see some similarities, right? It is just like fi by h, right? But instead of that, just another one more variable is used, j. Okay. So similarly, yeah, let's go to the next one. So similarly, you can find like the backward also. Dou f by dou x, the same at I comma j. Now backward, how you can write? Backward formula. F I comma j minus by, yes. So this is the backward difference. Why it is backward difference? We are using the not the forward point of x rather than the backward point of x. That is I. We are starting from I, but we are going back. That is I minus. Okay, that's the backward difference. So similarly, central difference also. So dou f by dou x So central, how you can write, just remembering the what you say, the derivative just on a single variable. Then yeah, but yes, so uh, tricky things will come. So so since I plus 1 and I minus 1, I plus 1 is here, I is here, I minus 1 is here. The difference between them is 2 delta x, delta x, delta x. So you have to divide by 2 delta x. Plus order will be like delta x square. Okay, so it's a good method. So this is like central. Okay. Okay. Similarly, you can have for the variable all the three methods. You just replace, now it will be the role of j, right? It is the role of j which will be varying, right? Understood? And you will be dividing by delta y. All the things are same. So this you can do. I comma j both backward, forward, central. You can write similarly. Okay, now a bit more interesting thing, which will be helpful in your partial differential equations. Well, we will be learning about partial differential equations. So that is the double derivative. Double derivative, not derivative like double derivative, but partial. So that is, we'll try to evaluate dou 2f by dou x2 at I comma j. What it will be? Anyone? So I will write one, then you can refer to the notes like how I wrote dou 2f by dou y2 and mixed derivatives like dou 2f by dou x dou y. Okay, I will write this one. So it will be fi minus 2fij, okay, plus fi minus 1j by delta x square, or you h square you can write. I am writing delta x so that you and y components. If you just write h, you might forget that it is only just one variable. Okay. So this is the forward. Okay. Forward. Similarly, you can write the backward, the central also for this. Anyway, so these are just some of the what you call the basic terminologies or formulas for the double derivative. Okay. Double derivative where you have more than one variable in picture. So it's like just like extending your ideas of single variable and two double variables. Yeah, that's it. Nothing new we are doing. Are we doing anything new? Since you knew the forward finite difference formula, backward finite difference formula, central finite difference formula, now you can extract some knowledge from that and apply it to the two variable case x and y. Okay. So yeah. I would like to apply an idea of interpolation and differentiation here, okay, where partial derivatives will be used a bit. Let us see. No, it won't be used. It won't be used, but I just showed you the a bit of what do you say, a bit of short hint of how partial derivatives look like. But after this, we'll go to integration, then ordinary differential equation, then partial differential equation. While going to the partial differential equation, you can appreciate these things, okay, like all these ideas. There it will be more clear. So you can see how the roots are following. We just learned derivative. While learning the first slide of derivative, I told you that differentiation is a gateway to understand like differential equations. Okay. Now differential equations, it will also be helpful to understand partial differential equations. Okay. So you can see how the root is spreading. So therefore, I'm saying each class is important. You just open your eyes, just listen. It will be clear. Okay. So this is already in the notes, but still I want to like just go through it a bit quick. Okay. So consider a slab. Okay. This is a iron slab. Okay. And say you are marking the point x equals to 0 and somewhere like here x equals to 20. Okay. Then here it is x equals to 10. Okay. All right. So this is your x direction. Okay. So now you have the plate got heated. Okay. So now you want to find the temperature profile. Okay. You want to find the temperature profile, how the temperature varies using the idea of differentiation and interpolation. Okay. So it's a bit of applied example. Okay. So what I will do, you don't know the function. Here you don't know the function. Here you can get the data points. How you will get the data points? You can measure using a tape, that is what is the x coordinate, start left to right. And at each point you can place a high-end thermometer and measure the temperature. So at each point you can measure the temperature and get the data. Okay, so these are the data sets. Say at x equals to 0, 10, and 20, I have the data. Okay, what is the data? That is T of x. That is T in Kelvin. Okay, so it is 350 and 450. Okay, this is the data set. Now our goal is to find what is the temperature profile. So aim is to find the temperature profile. Okay. So temperature profile T of x. So you can only find the temperature profile if you know how the temperature varies with respect to x, how the varies with the length. Okay. If I want to find a temperature somewhere here, then you just find that x and substitute that x in your T of x. So just by knowing the temperature at few of the points in the iron slab, you can find the temperature profile. This is the benefit of numerical methods. So for this, we will use Lagrange interpolation, okay, which I think you already covered in your previous semester. Okay, so idea is use a Lagrange polynomial. Okay, so that means we will assume that T of x is represented by like Li of x and f of xl. Okay, where Li of x are your Lagrange polynomials, right? So how it will be? Since we have 3 points, we are going from 0, 1, 2. 4 points, and we could have gone up to 4. So that means it will be L0 x fx naught plus L1 x f of x1 plus L2 x f of x2, right? So how these Lagrange polynomials they look like? Any ideas from your previous semester? How Lix looks like? Yeah. Anyone volunteer? Okay. So I just write it if you can remember j equals to 0, j not equals to I. And since we have 3 points, I will go till 2. Okay, 0, 1, and 2. Then it will be x minus xj by divided by xi minus xj. I think you have seen somewhat similar in previous semester. Okay, so this is your Lagrange interpolating polynomial. I urge those who are new to this course to read about this interpolating polynomial, Lagrange interpolation. Okay, then it will be easier for you. And even those who are not new, I still ask them to go through. Okay. So similarly, so what is the benefit of this? That means from this, we can find L0, we can find L1, we can find L2. Now, that means I equals to 0. If I equals to 0, that means j can't be equal to 0, j not equal to I. So j has to start from 1 and 2. Okay, but we need the value of I, that is 0. So we can follow it, right? So j starts from 1. That means x minus x1 by x0 minus x1 times x minus x2 divided by x0 minus x2. Isn't it? Is it correct? Yeah. Similarly, can you find L1 of x? So L1, that means I equals to 1. That means according to this formula, j can't be equal to 1. Okay, so j can be 0 and 2. All right. Yeah. So that means x minus x0 by xi. I means 1 minus x0 times x minus, can it be 1? Can x minus x1 be there? So it will be x minus x2 divided by what it should be? x1 minus, yeah. So similarly, can you write L2x? So I equals to 2. So that means j can't be equal to 2. So j can be 0 and 1. Okay. So that what you can write? J can be 0 and 1. So x minus x0 by x2 minus times by, that's it. Okay. So if you just think, it will be normal. Okay. So now there is an important observation to make. Okay. Just by calculating this, we are not doing just calculation, but just make an important deduction physically. So observe that these LIs, okay, these LIs, they don't depend on temperature. They only depend on the position X. Is it right? Are they depend on temperature? Does it depend on temperature? They depend on X. X is the position. Okay. So this is one of the important points. So whatever Lagrange polynomial you take, any polynomial you take, it won't affect. Okay. Okay. So can you substitute all this x0, x1, and x2? So after you substitute x0, x1, x2, you know x0, x1, x2, right? Those are given. x0 is 0, x1 is 10, x0 is x2 is 20, right? After you substitute all this, then like I'm just writing, check it. L0 x, you will get around like 1 by 200 by multiplied by x minus 10, x minus 20. What is L1x? So these things you have to do. Okay, so L1x, you can write like find at your home, like are these actually correct? Similarly, L2x, x by 200 into x minus 10. Okay. Now, temperature profile, that is temperature profile, which is T of x, is summation of Lix into Fi, right? Fix or f of xa. So yeah, you should tell. So yeah, that L0 we know, but what are Fi? So you can write it as like 300 L0 x plus 350, right? L1x, I think, plus 450 L2x. These are the temperatures. Fi are the temperatures, right? Temperatures of those data you have gotten. Up to this is clear, right? Now you found the temperature profile, is it? Now you found the temperature profile. So now that means at any point X you ask me, I can provide you the temperature at that point of the slab. That is the main motivation behind this. So you do the calculations, then I'm writing just the final one. You will end up here 1 by 4 x square plus 10x plus 1200. Okay. I request like you just plot it. It might look like a quadratic parabola. Okay. X squared. Just plot the temperature profile, how it looks from x equals to 0 to say x equal to 50 or something. So there here, so I just did a problem on interpolation. Where is the derivative coming? Why I did? So something like if you know, I don't know, it's like Fourier law of heat conduction. Okay. Fourier's law of heat conduction. You don't need to remember this, but I'm just saying how to where numerical methods go. Okay, crossing different branches of science. So what it says is the heat flow rate per unit area. Okay, heat flow rate per unit area in a one-dimensional slab, which is in our case, is given by to minus k dt by dx. Okay, k will be given to you. It will be given to you. dt by dx you have to find, but you know already t of x. Now it is easier for you to find dt by dx. It's the first concept we applied in our class today. Once you know the polynomial, interpolating polynomial, you just differentiate. And that's it. So your job is to find q at x equals to 0. Okay. What is q at x equals to 0? So what you have to do, dt by dx. So you will get a linear equation because t of x is a quadratic equation, right? So dt by dx will be a linear equation and it will have x. Okay. And in that, in place of that x, you can substitute x equals to 0. And that you got dt by dx at x equals to 0, right? And then you already have k. Oh, I did not mention k. So k is a constant which is like 100 watt per m. So up to you. Like this is a exercise for you. It's an exercise. Find q at x equals to 0. So finally, like your answer should depend on watt per centimeter square. What is q? dt by dx. You find the unit. Okay. So we have come to an end of differentiation topic. Okay. Now we'll move to integration. Okay. Okay. So we'll start with the numerical integration. Okay. So we will be covering few of the methods. We'll be learning about trapezoidal rule. Why it is trapezoidal, you will know. Simpson's 1/3 rule. It is invented by Simpson, so it is Simpson 1/3 rule. Simpson's 8/3 rule, 3/8 rule. Okay. Then a generalized version of all this. Then we will be able to understand these are all coming under a general case known as Gaussian quadrature. What is quadrature? Gaussian is name of scientist Gauss. Quadrature is another name for measuring the area. Integration, you already know integration. What's the interpretation of integration? It's area. Computing the area. Okay. So here, integration is not like the usual integration we have dealt in our class 12th. Okay. Integration of functions is more difficult than differentiation. And integration here, especially numerical integration, we are dealing with numbers. So it can't be an open integral. It has to be a closed integral. That means it has to be a definite integral. That means it has to have the lower limit and the upper limit. So we will be dealing with integrals of this type. That is the definite integrals. Okay, because these are numbers and numerical integration is all about numbers. We can't have these limits. Without these limits, we can't solve the integration using numerical integration methods. Okay. You need to have definite integral to solve this. Okay. So usually analytical investigations or analytical integrations, they are done over a set of functions, over functions. Okay. But numerical integrations, you will do over a set of points. Okay. So how? Same method or same idea we will apply as in the differentiation case. In the differentiation, what we did, we used interpolation to find the approximate polynomial over the set of data points. Then we have the polynomial. Then what we did, we differentiated that polynomial. Okay. After you differentiate the polynomial, which point you want the derivative, you can substitute that value and you get the derivative, right? Value of the derivative. Same idea we will apply here. Set of points. Okay. Then you have the polynomial. Then you can integrate it. You can differentiate and integrate a polynomial. Given a polynomial, you can easily integrate, right? Okay. So as I was telling, knowledge of interpolation will be again helpful in understanding numerical integration. So I urge those students who are new to go through interpolation techniques. Those are written on the board, these three interpolation techniques. So up till now, we have covered these three interpolation techniques. So I urge you, like, read them again, go through them again. Okay. So just here in this course, like, we will talk about definite integral. Okay, that is integrals of this form. We can also similarly compute definite integral like double integrals. I think you also know about double integrals, right? Yeah, no? So if it is a function of two variables, it is a double integral. This also we can solve using various numerical methods. Okay. All right. So you can see the figure on the right? Function like f of x. Okay. Yeah. In blue, you can see that, right? Then I know only about 2 points, A and B. Okay. If you have only the knowledge of 2 points, okay, then you can fit that line, right, using a straight line. So you have A, corresponding to that you have f of A, you have x equals to B, corresponding to that you have f of B. Okay, the best you can do is fit a straight line. Okay, by fitting a straight line, we are saying that we'll integrate that straight line equation and over that interval A to B, and we'll find that area. Okay, if you find that area, what area it will be? It will be this area, right? It will be this area, right? But what is the actual area? Actual area is above this, like this guy, maybe, yeah, just below the blue curve. So you can see a lot of errors are creeping in. So this whole thing, this is missing. This whole area is missing, right? So you can easily see that using this method, we are encountering error in our numerical method scheme. And since this guy looks like a trapezoid, okay, A to B, FA to FB, this looks like, say, trapezoid, right? So it is known as a trapezoidal group. So it basically is the area. So now this is the basic idea. Now we will do when we will see the math behind it. Okay, how it looks. So again, same as before, like you can apply the previous formula, like y is the function fx, and you can approximate it by li f of xi. This is the same thing we'll break or after the break, I think. So I equals to 0 to n, but here it will be like only 2 because you have only 2 points. So say like x0 to x1, maybe like a to b I am writing fx dx can be written as, any ideas? It can just integrate it, right? F of xi will come outside because it will be a number. What will be integrated? Li's, because it's a function of x. Li we just saw previously that it will be a function of x. So how you can write it? Say f of x0 will come outside, then you will integrate L0. L0 will look like x by x0 minus x1 dx. Okay. Plus then f of x1, right? Integration of L1 dx. What is L1? But you have to like, am I doing something wrong? I have not mentioned the limits. Did you understand this thing? See, y is a summation of Li fxi. Okay, that means it is L0 f0 plus L1 f1. Okay, now you are taking the integration of fx dx. That is this is not equal to exactly. This is an approximation. So that will be f of x0 or f of x1 will be numbers, because you know x0 and you know the value fa and fb, f of x0 and f of x1. So those are numbers. Outside of the integration, you can take it, right? Then what will be inside the integration? The function remaining. That is Li of x. Before we just looked into this form of L, right? Yeah. So it is a function of x. So it uses the idea of interpolation again. Okay. So again, just I request you like to go back and especially read these three interpolations. Okay. So if you do this just by substituting like the if you just solve this integration, I think you can solve this integration. X1 minus x0 is again a constant, and it will come out of the integration. It is a number x0 x1 it is given to you. So x minus x0 will only be there. Okay. Check again that if you do in this manner, you will land here like this. You can simplify to this state. Okay. Now, can you say what is this? Look carefully. X1 minus x0 is like b minus a here, right? And fx or addition of these heights. So that's like an area of a trapezoid. Even if you learned the area of trapezoid in your class, some class, 6th, 7th, 8th, you might have forgotten. Again, remember. Okay. Remind yourself that this is the area of trapezoid. So if I want to give these names A, C, and D, then this is like the area of trapezoid. Okay. Sorry. A, B, C, D. Hence, we have the trapezoidal rule. Okay. But I warn you that this is not the bit of accurate method, because you already can see that these are the areas which are creeping in. Okay. Like this is the remaining area which should have taken into account, but is not taken by this numerical method. So therefore, not a accurate method. The errors of all this in like next class, we'll skip the error for now because it will be a bit of more critical. But it's up to you. If you want me to cover the errors, I can cover. But I can just say that it is a order of third order error equation. Like this will be plus order of h cube. Okay. But then you should have asked me the question, oh, order of h cube is like very small error, right? But this is just with 2 points. You will see this is just a local trapezoidal rule. There is another rule which is known as a composite trapezoidal rule. That means this guy, we can dissolve A to B multiple segments, okay? Which you do normally in Python like linspace, A to B, how many points you want to divide, okay? Now for each of these two sets, you can like approximate via a trapezoid, okay? That is known as a composite trapezoidal rule. Those things, of course, you have to try using Python. If you take 100 different or 200 different points, then It's not reasonable to do it by hand. You can use a for loop and do it by Python. Okay. Okay. So this is what I mean. Okay, this is what I mean about the composite. Okay, composite trapezoidal rule. So instead of just like one trapezoid, you are seeing multiple trapezoids, right? See A to B, but I have this one trapezoid, another trapezoid. So multiple trapezoids are there clubbed together. Okay. So therefore, it's a like composite trapezoidal. Okay. So just to be like maybe I can say this is x naught, this is x1, this is x2, so on, and say this is xn equal to b. Okay. So you can write, say this is y equals to f of x. Okay. So, and this is y, this is x. Okay. So say like you are trying to integrate from x0 to xn, that is from a to b. Okay. Y dx or fx dx. Then how you can do it? You need to, you know this, right? This is the additivity rule of integration. X0 to x1 maybe y dx plus then x1 to x2 y dx, so on from xn minus 1 to xn y dx. To understand, because you are taking the whole integration as the function of each of these areas. Okay, right? And these are the errors which you have crept in. These are the errors. These are the errors which your formula is not able to take into account. This blue guy is actually the y equals to fx. This blue guy is actually y equals to fx, and this red one is your interpolation polynomial, interpolating polynomial. Okay, and you can see that these are made of piecewise lines. Okay, that is what is interpolation. Okay, just for simplicity, we can assume that x1 minus x0 is same as x2 minus x1 and so on till xn minus 1. That is like h. That's the step size, uniform step size I'm taking. Okay. Now I ask you, like, just from our previous trapezoidal rule formula, can you say for any general trapezoid what's the like formula? Like xi, to say I go from xi plus 1, I do y dx. Can you say me what will be the formula? That means some xi is there, some xi minus 1 is there. I have a yi, I have a yi plus 1. I need the area of the trapezoid, right? That local trapezoid. If I know that local trapezoid, I can sum it over all the i's and I can cover all the trapezoids. If I cover all the trapezoids, then it will be a good form. Yeah. So therefore, I am generally writing this statement. Generally, starting from xi to xi plus 1, y dx. What will be that? No. It's just from xi to xi plus 1. That means it is just for this one trapezoid. Just one. Say this is xi and this is xi plus 1. Just one trapezoid. So it will be like h by 2, xi minus 1 minus xi, that is h. Okay, by 2 times yeah, plus yeah. So yeah, what's your name? Alapi. Some names I have seen while marking and all those things. Some names I remember. I should remember the name of the. Okay, so it should be yi plus 1. Okay, sorry. So for any general interval xi and xi plus 1, we are just integrating that trapezoid y dx. So it is just given by h by 2 yi plus 1. You know why I'm doing that. H is just the x width and yi plus 1 are the sum of the heights of the trapezoids. Okay. Now my question is, can you compute x equals to x naught till xn y dx using? See, you found the general formula for this, right? Now I think her statement applies that we will take a summation. Okay. So what you can do, you can apply this equation number 1. You can apply this equation number 1. Okay. What it says, x naught to x1 y dx. That means it will be h over 2 y naught plus y1 plus x1 to x2. What will be h by 2 y1 plus y2, so on till plus h by 2 yn minus 1 plus yn, isn't? Now we can't write this way, right? We have to write in a general like way. Can anyone suggest like it will be h by 2? Summation we can write, but first let us write in a more open form, then we can generalize. So y naught is not appearing anywhere else. Is it appearing anywhere else? No. So let us keep y naught plus y1 is appearing. So what I have to do? Plus so on up to yeah, Dikhil was right. 2yn minus 1. Yeah, but there will be 1 yn. Yeah. So this is the trapezoidal. So, but if you go a bit more, I can tell you that if you compute the error for this, it will be a second order accurate. Okay. So globally, if you do it, if you take more trapezoids, okay, just instead of just one, okay, then this is a good method. So this is the trapezoidal rule. See in Python these rules, but just need to remember the method. It's the area of a trapezoid. So what it comes to your mind is x length, that is h, divided by 2 times the sum of two heights. Height at one point plus height at the second point. That's what we have written, and you have to sum it up. Okay. All right. So there is another method which is more interesting and also more accurate. Okay, developed by Simpson. Okay, it is known as Simpson 1/3 rule. But why it is known as 1/3, we'll come to know after we derive the formula. Okay, so this sorry for this. So this is actually f of x. Yeah. So f of x, and these are the points. The yellow points, they denote the points where we know the data. Okay, where we know the data in set of discrete points. Okay, and this is the one in bold is the function fx actual. Okay, and this one, the set of data points we approximate using the interpolation in polynomial. That is the dotted lines. Clear? You can obviously see there are some errors creeping in because the area, again, you have to integrate. It will be these areas, right? Not these areas will be ignored. Okay, so therefore you can see where the errors are creeping in. These are the points where the errors are creeping in. Okay, so this example I had set for Simpson's 1/3, and this one I have set for Simpson's 3/8. But we'll see. We'll return to this figure again. Okay, but how many points we have taken? So generally, I would say this. After learning these methods, we will come to this, which is the Newton Cotes or Gauss quadrature formula. Okay. Integration x naught x and y dx can always be written as a summation I equals to 0 to n wi f of xi. It uses the function value at each of the data points, and there will be some weight associated, wi. Different terms of wi gives different numerical methods, okay, for integration. Okay, this is the main take-home message, okay, for numerical integration. Okay. Or you can even see for trapezoidal rule, this wi is different. For Simpsons, you will see this wi will be different. Okay. So instead of just 2 points for our trapezoidal rule, we took 2 points, right, for trapezoidal rule. Yeah. Instead of 2 points, we say our approach can be even more accurate if we take instead of 2 points, 3 points. If points, we can approximate the data points a bit more accurately, right? So therefore, like what happens if we take instead of 2 points, 3 points? Okay. So again, the same concept, See, y equals to sigma. And how many cases you need to go? I equals to 0 to 2. 0, 1, 2. 3 points you have. Okay. So x naught, x1, x2, and you will have fx naught, fx1, fx2. And you will be knowing L naught, L1, and L2. Is it okay? Yeah. So for Simpsons, this is Simpsons one. Why it is named as 1/3 rule. Okay. So again, like why I am saying as L naught f of x naught, you know x naught, you know f of x naught. You will have to find L naught, L1, L2. L1 f of x1 plus L2 f of x2. Right? This is our whole formula. Okay. Then we will integrate this. Okay. But before that, you have to find these LIs. Li, you remember we discussed the heat problem. Okay. There we have defined this Li. What it will be? Equals to 0 to n, and j can't be equal to I, then it will be x minus xj by xi minus xj. We know this formula already. Okay. Now, depending on this formula, you have to. Okay. But in our case, it will be just j equals to 0, j not equals to I, until 2, 0, 1, 2, we have 3 points, and x minus xj by xi minus xj. Right? We have 3 points. So up to that only we will take. Why will take up to n, right? So yeah, can you say what is L naught? I equals to 0. That means j can't be equals to 0. J only has 2 choices. J can be 1 and 2. For j equals to 1, what you will have? J equal to 2. Yeah. Observe this pi. What does this pi mean? You are taking multiplication. Therefore, we are multiplying. Okay. Right. Similarly, you can calculate L1 as I'm just writing the direct result. You can see this. Okay. L2 is like again x minus x naught by x2 minus x naught times. Yeah. Any issues? So you now know L0, L0, L1, and L2. So what you can do, integration of y dx, say from x0 to x2 is just equal to, take this equation in mind. Take integration on both sides, left side and right hand side. Then what you will get? F of x0 is a constant. So it will just be L0. So it will just be L0 dx. right? From x0 to x2, f of x1, x0 to x2, L1 of dx, plus f of x2, L2 dx, right? And you know the forms of L0, L1, and L2. Okay. So again, since it's, you know what is x1 minus x0, you know what is x1 minus x2. These are just h. x1 minus x2 will be minus h. But yeah, x1 minus x0 will be h. Okay. So those things you have to substitute. Then you can show there is a bit of just algebra involved. Then you can show that integration x0 to x2 y dx equals to like h over 3 f of x0 plus times f of x1 plus f of x2. Okay. So given 3 points, you can approximate the integration in this. Used everything we have in our box. Like we have h, we used it. F of x0, f of x1, f of x2, we used it. So just remember these coefficients 1, 4, and 1. Now I bring your attention to this formula. See, Wi is multiplied f of xi. Wi is a weight. Here you can see what are the weights. So in trapezoidal rule, I ask you to compare the weights for the similar thing. The Wi's will be different for the trapezoid. The Wi's are different for the Simpsons. That's how different Wi's will give you different numerical for integration. That's I have written here. Okay. Okay. So similarly, you can write composite Simpsons rule as well. Okay. So can you say how the composite rule looks like without even doing any writing? Now you have to take small interval and add them up, right? For composite. So what you will do is starting point will be say x1, x2, x3, then x2, x3, x4. Okay. So similarly, I want to come the trapezoidal group, but it's very simple. Like it's not that difficult. X0 to x and y dx. Can you say to me what will happen? So same h by 3 will be there. That's for sure, right? Then f of x0 plus 4 f of x1 plus that's where the trick is. Okay. Another patch will be added up. So again, see why in the trapezoidal rule it 2 came. When you added it 2 came, right? Parts when you are adding, 1 is getting overlapped. So there is a 2 times multiplication. Okay. So therefore, like I urge you to look into this. I can write this like 4. Again, it will be f of xn minus 1. Plus again, the n term will remain as it is, like f of xn. It doesn't have any pair to pair with. Okay. Right. Yeah. So before we go to the 3/8 rule, I want to show an example in Python, okay, where we compare these things. But before that, what is the problem we are considering? Okay, what is the problem we are considering? We will consider a problem. You already know the answer. Okay, then we can compute that whether we are right or wrong. Okay, say like we have this x and y, okay, in the plane, and you know a circle, right? You know the circle. So just this half of the circle and the radius is 1. So x will be 1 here. And of course, y will be 1 here as well. Okay. I'm just taking 1/4 of the circle. Okay. So we can calculate the area of this one. Okay. And we'll multiply this by 4. Then it will be the area of the circle. That's the basic idea. Okay. You know the equation of the circle centered at origin is x square plus y square equals to 1. Okay. So similarly, like what you can do is, so area of the circle is like pi r square, and we are taking r equals to 1. If r equals to 1, so the area will be just pi, and you know pi, the value of pi. Okay. So our aim is to find the value of pi. Without solving for pi, we want the value. So our aim is like pi is equals to 4 times this area, quadrant, right? The area of this quadrant. Is it 4 times integral 0 to 1 y dx? How it is? We will take, it's just class 12th math. Okay. We will take a small strip. The height is y. This is the strip is dx, and this area will be y dx. We are approximating it by a rectangle, so y dx, and this strip we want to take from 0 to 1. Okay. So you can and what is y? What is y? Yes, that's correct. Root over 1 minus x squared dx. Okay. Now you know how to solve this integration. Okay. You know how to solve this integration analytically. Now we will solve it using Python. Okay. Using two different methods: Simpson's 1/3, Simpson's 3/8, and trapezoidal rule. Yeah. So yeah. Take the summation of each of these terms. Okay. So you can see I have defined my function f as a lambda function, lambda x, square root of 1 minus x square, which we have just written in the slide. Okay, that is our function. We have to integrate, and we know we have to integrate from 0 to 1. Okay, so empty dot square root 1 minus x square I have written. All right. Then I'm defining trap, a variable, as fa plus fb. You know that those things will. Okay. So this is a clever coding. This is a clever coding. What I did, I will store the integration result in the variable known as trap. Okay, trap for trapezoidal. In the trapezoidal rule formula, you have taken FA and you have taken FB. Okay, those are the only terms which are not multiplied by 2. Other remaining terms were multiplied by 2. Okay. So therefore, I am saving them already before. Then I will just do 2 times of those internal terms in the loop. Okay. So trap equals to FA plus FB. What is FA and FB? These are Y0 and Yn. Okay. I am saving them already. Okay. Then for I in range 1 to n, okay, you can see x equals to a plus I times h. That means every time a for loop runs, it will take new x coordinates, right? Till yeah. So then what you do? You already have trap as FA plus FB. Okay. Then you simply have to do 2 times fx, 2 times f at the internal x variables. You understood what we are doing here? Yeah. And after the for loop is finished, then we come to the next step, which is out of that indentation. Okay. Trap equals to trap times h by 2. We never did a multiplication by h by 2 before. So we did it in fine. So actually we covered the full trapezoidal formula through this code. Okay. Then times of the trapezoid, 4 times of that quadrant. Okay. That should give us pi. Okay. It's already giving I'll again run in front of you. I think again it will be pi only, but again 3.14. Okay. So that's like you're getting up to 12 or some decimal places. Yeah. So same example I want to do. Same example I want to do using Simpson's 1/3. Same function. Same function. So Simpson's 1/3 I want to explain, like see, a equals to 0 to 1, same. N equals to 100 is same. H equals to b minus a by n, same. Now Simpson 1/3 variable stands for Simpson's 1/3. I will store the integration value here. Okay. Again, Again, the same strategy. FA and FB, I am storing, adding and storing previously, okay, beforehand. Then I am doing the looping, okay. But here there is a catch. Here there is a catch. Simpson rule will sorry. What I meant to say is, if you work out the Simpson's closed form formula, you will see which terms are multiplied by 2, check. Which terms are multiplied by 4, check. Then accordingly, you can derive this condition, okay. So if the indices are even indices, that means I mod of I comma 2 is 0, okay, then you multiply 2 times of x. If it is not the case, then you have to multiply 4 times of x. You have seen the coefficient 4 in Simpsons, right? So then h by 3, we are doing h by 3 in Simpsons. H by 3, and the formula we have fa plus some coefficients are 2, some coefficients are 4. So that's how we told the computer, we told Python that yes, you do it this way, then it is doing automatically. For how many points you want? 100 points, you can go for 1000 points also. Okay. So print again, Simpson 4 times Simpson. So again, it gives the pi. Okay. So Simpson's 3/8, I think I will stop here, but we'll try to cover Simpson's 3/8 next class. Okay. Why we say 3/8? Because again, 3/8 will come in the formula of the integration. Okay.